You know, inside every single atom, there's this incredible cloud of electrons just buzzing with energy. But it's not chaos, not at all. There's a beautiful, hidden order to the whole thing. So how in the world do we find one specific electron in that buzzing cloud? How do we describe where it is and what it's doing? Well, that's exactly what we're going to figure out today by learning the secret code of the quantum world. So this is the big question for today. You can't just slap an XYZ coordinate on an electron like it's a spot on a map. Oh no, the quantum world is way stranger and, honestly, a lot more elegant than that. To find an electron, you need its unique four-part quantum address. Okay, here's how we're going to tackle this. First, we'll get our heads around this whole idea of a quantum address. Then we're going to break it down piece by piece. We'll start with the big picture, the principal number, n. Then we'll zoom in on the shape and orientation with L and m sub L. After that, we'll look at the electron's own unique property, its spin, m sub s. And to make sure it all clicks, we'll wrap up by solving a problem together. So here is the most important idea to grab onto. Just like no two houses can have the exact same street address, no two electrons in an atom can have the exact same set of four quantum numbers. It's a fundamental rule. This code tells us absolutely everything we need to know about that electron, where it lives, what it's doing. It's basically the blueprint for its entire existence.
Let's build this address right now. First up, you've got the principal number, n. Think of this as the state. It gives you the general energy region, the big picture. Then we get more specific with the azimuthal number, L, which is kind of like the city. It defines the shape of the electron's neighborhood. Next, we find the magnetic number, m sub L, which is the specific street, how that neighborhood is oriented in space. And finally, the spin number, m sub S, is the house number, which makes sure we can tell it apart from its next-door neighbor.
Let's start with the first and biggest piece of that address, the principal number, n. This one really sets the stage for everything else that follows. So the key thing to remember about n is that it can only be a positive whole number, 1, 2, 3, and so on. It can't be 0, and it can't be a fraction. And why is that so important? Because it means energy levels in an atom are quantized. They come in these distinct steps, like rungs on a ladder. You can be on rung 1 or rung 2, but there's no such thing as being on rung 1.5. And as that number n gets bigger, going from 1 to 2 to 3, the electron is climbing higher up that energy ladder. A bigger n means the electron shell is larger, it's generally hanging out further from the nucleus, and it's packed with a lot more energy. It's like climbing away from the atom's center, one energy level at a time. Okay, so we know which energy floor our electron lives on in this atomic skyscraper, but what's the layout of that floor? Is it just one big open space, or is it divided into a bunch of smaller, weirdly shaped rooms? Well, that's where our next two numbers, L and m sub L, come into play. The second number, L, is all about the shape. Is the electron's home a perfect sphere, or is it more like a dumbbell, or maybe something even more complicated and wild? This number, L, gives us that architectural blueprint. It's the city part of our address, defining the whole character of the neighborhood. Now here's where it gets really interesting. There's a rule. The possible values for L are totally dependent on n. And this isn't just some random rule they made up. It tells us something really profound about how atoms work. It means that as you go to higher and higher energy levels, as n gets bigger, you unlock the potential for more complex orbital shapes. The floors in our atomic building get way more architecturally interesting as you go up. Our third number, the magnetic quantum number m sub L, takes that shape we got from L and tells us which way it's pointing in 3D space. So if L told us we're in a dumbbell-shaped city, m sub L tells us if that city's main street is pointing up and down the x-axis, the y-axis, or the z-axis. It nails down the orientation. And yep, you guessed it, we see another dependency here. The number of possible orientations, m sub L, depends entirely on the shape L. So a super simple spherical shape, where L is 0, has only one possible orientation. M sub L has to be 0. But a dumbbell shape, where L is 1, can point in 3 different directions, represented by -1, 0, and +1. You can see how the atom starts to build up this incredibly complex, 3-dimensional structure just from these simple rules. And this table just lays it all out perfectly. Now, scientists have some shorthand for these shapes. An L value of 0 is called an S subshell. That's the spherical one. An L of 1 is a P subshell. That's the dumbbell shape. So if you look at the row for n equals 3, you see that L can be 0, 1, or 2. What that really means is the third energy level contains an S neighborhood, a P neighborhood, and a D neighborhood. It's a collection of 3 totally different types of communities. So, we've got the energy level, the shape of the orbital, and which way it's pointing. We've pinpointed a single street. But here's the catch. Each one of those orbitals, each street, can actually hold 2 electrons. So how do we tell those 2 apart? Well, that brings us to our fourth and final quantum number. This is the spin quantum number, m sub s. And what's so cool about this one is that it has nothing to do with where the electron is. Instead, it describes a fundamental, built-in property of the electron itself, just like its negative charge or its mass. The easiest way to think about it is that every electron has a tiny internal magnet that can only point in one of 2 directions.
And the options couldn't be simpler. That little magnet can be spin up, which we give the value of +1/2, or it can be spin down with a value of -1/2. That's it. Those are the only 2 choices. This is the final house number in our address. So if you have 2 electrons sharing the exact same orbital, one has to be spin up and the other has to be spin down. This guarantees that every single electron has a truly unique address.
All right, we've gone through all 4 numbers and the rules that tie them together. Now for the fun part. Let's see how this all works in practice with a real example. This is where the theory really comes to life. So here's our puzzle. If we're looking at the third energy level, where n equals 3, how many individual orbitals, how many of those streets are there in total? We can figure this out just by using the rules we've already learned. Let's walk through it. Okay, first step. If n is 3, what can L be? Remember the rule? L can be any whole number from 0 up to n-1. So for n equals 3, L can be 0, 1, or 2. Easy enough. Now we just look at each of those L values. For L equals 0, the S subshell, m sub L, can only be 0. That's 1 orbital. For L equals 1, the P subshell, m sub L, can be -1, 0, or +1. That's 3 orbitals. And for L equals 2, the D subshell, m sub L, can be -2, -1, 0, +1, and +2. That gives us 5 orbitals. So now we just add them all up. We've got 1 orbital from the S subshell, plus 3 orbitals from the P subshell, and 5 from the D subshell. And that gives us a grand total of 9 orbitals in the n equals 3 shell. And hey, want to know a cool shortcut? The total number of orbitals in any given shell, n, is just n squared. So in our case, 3 squared is 9. It works every single time. See? That's the elegance of this system. And here it is, the whole shebang, all in one place. This table is your ultimate cheat sheet for an electron's quantum address. You can see the entire story right here, starting with the principal number n that defines the overall shell, all the way down to the final spin, m sub s, that makes each and every electron unique. It's this perfect logical system where each rule builds on the one before it. So we'll leave you with this final thought, this rigid set of rules, this fundamental law that no 2 electrons can have the same 4 quantum numbers. What does that actually tell us about the world? It means that matter can't just collapse in on itself. It forces electrons into these different shells and subshells, which creates structure and complexity, and ultimately it creates the entire beautiful diversity of all the chemical elements. The address isn't just a label, it's the blueprint for the entire universe around us.